This video will show you how to use the Vivado toolchain to create a simple digital circuit. So go ahead and open up Vivado. I have Vivado 2018.2. When you open it up, you'll see a welcome screen where you can create or open a project. Since this is our first project, we will create a project, but you can use this same project for all of your labs. So in subsequent openings of Vivado, you can just open your project. Click Next. We'll call this project CPE 133 Labs, because as I mentioned, we can use this one project for all of our labs. And put it in a location where you'd like to be able to find it again on your computer. It's an RTL project. We don't have any sources yet, so we don't have any to add. So keep clicking Next until you get to the default part. The part we are using is the chip on the Basis 3 board, which is the XC7A35TCPG236-1. This number is on Polylearn as well as the Basis reference manual, as well as printed on the FPGA on your board. But since we will use the same project for all of our labs, you'll only have to enter this once, unless you create another project. Then we click Finish, and a project is being initialized. So the sources window is pretty important, so I like to hide this properties window so I can see my sources. Notice we will be creating three types of sources: design sources, constraints, and simulation sources. Every design source can have a corresponding simulation source, but there is only one constraint file, and that constraint file is to map whatever you are using to the Basis board. Okay, so let's start by creating a design source to design a simple digital circuit. The circuit we'll design in this example is this circuit shown here with these three gates. It's also described by this truth table to the right. So we need to create a circuit that has a NOR gate, an AND gate, and an OR gate. It has inputs A, B, and C, and output Q. So let's go ahead and say add source, add design source, create file, and we always want to choose file type of System Verilog because that's the language we'll be using in this class. And the file name, we'll call this lab 0, or whatever name of your black box that you have designed, and then finish. Now we can enter in the port names A, B, C, and Q, output for Q, and click OK. Now we can open our file that was created. And the first thing you always want to do is fill in the header information, which there's a lot of things you can fill in, but I just like to put in my name, the date, and a description. So this is a dummy circuit to illustrate how to use Vivado. It's useful to do this right away so you don't forget to do your header. Header is really important because if you ever come back to your file years from now, it'll give you a good quick description of what you were trying to do. Okay, so notice that Vivado's created a template for us of our black box model. It has the name of the model as well as the ports. And so now, in between the semicolon and end module, we can enter what is inside that module. So we have to create those gates. So we will use the assign statement, and we will assign Q to be A NOR B, ORed with B and C. So A NOR B, we do A or B, and that needs to be NORed, so we'll put a not in front of that. ORed with B and C. And you end every statement with a semicolon. So there you have it. We just implemented this circuit. Okay, so notice that we have a squiggly line here. That squiggly line is telling us we have some kind of error. It says syntax error near AND, System Verilog keyword and used in incorrect context. So that's not how you write and in Verilog. You use a symbol, which is the ampersand. Now that squiggly has gone away, and hopefully we are now all good with syntax. So if you ever have a syntax error, for example, we forget a semicolon, usually Vivado will come up with a little red squiggly line, and you could hover over it to see the error. Other times, you might have to run your synthesis for it to give you a description. So let's just go ahead and do that. Let's say we didn't see a red squiggly line and we went ahead and we run synthesis. This is to check the syntax. Let's just say save and OK. And it's running our synthesis. And then we can click on this Messages tab and go down. It's sometimes helpful to just only look at the errors, turn off other things. It says syntax error near end module, and then you can often click on the link, it'll take you there. And it's like, I don't know what that error is. It's near here. Oh, I'm missing a semicolon. So it doesn't always tell you exactly what's going on, but at least it might give you some indication. Alright, so let's say we fixed our error. Now let's run synthesis again. Okay, great. Synthesis completed successfully. So before we go ahead and run implementation, we want to simulate this circuit. So we'll hit cancel. And now we need to add a simulation source. So we'll do add sources, add or create simulation source, create file, and again choose System Verilog. And always give your simulation file the same name as your module that you just created, which we called Lab 0, and then the word sim. So you know it's simulating that module. Finish. Now a sim file doesn't have any ports, so we'll just say OK. And now we can go under to the simulation sources, and there it is, Lab 0 sim, double click. And once again, fill in your header information. And in this case, I don't really feel the description's that necessary because the name of this file says it all. This is just a file to simulate my Lab 0 module. And there it is. We've got our blank template, which is not very helpful. So to help you remember what needs to go in a simulation file, go to Polylearn, and under week 1 there's a simulation template. So the first thing you need to do is declare the inputs and outputs to give to the module you are testing, and these can be the same name as the ports of your module. So in our case, our module has ports A, B, C, and Q, so let's just go ahead and use those names. If we had X, Y, and Z, and F, we could use those instead. But we'll go ahead and, I guess I'll just type them. Logic A, B, C, logic Q. You can put them all on the same line. I tend to like to put my inputs and outputs on separate lines. Then the next step is to instantiate your module under test. So let's try this again to copy it in as a template. There it is. So this begins with your module's name, which in our case is Lab 0, then a name for the instantiation, which you can call whatever you want. I'll call it Lab 0 instantiated. And then you list all the ports of your module, which are A, B, C, and Q, and then you want to link them to these variables that you declared, which we called A, B, C, and Q as well. Now, if we did call this X, Y, and Z, this X, Y, and Z refers to these pieces of the instantiation because the dot A is inherent to the port of Lab 0, whereas what we put in the parentheses is what we are connecting to it, which in this case we're calling X. So I'm just going to go ahead and keep my A, B, and C's. Okay, the next step, if we go to our next step, is to list our test cases. So again, I'll just copy this in as an example and then I'll modify as needed. Alright, so basically you write the word initial to say just run these test cases once through and then begin, and then it helps to have a truth table if you have few inputs, or at least a test case table so you know what you're going to be typing. So we start by listing all of our test cases. In our case, we want to list all of the lines of the truth table because then we will have fully tested this module. And that's possible when it's such a small module like this, but when you get to larger designs, you'll have to just pick a few test cases that you feel represent common cases of the module that you'd like to test. Okay, so notice we're going to go through 8 different test cases, running through the 8 possible combinations of the inputs, and then these are the outputs we expect. So here are input 0, 0, 0, and the output I'm expecting for 0, 0, 0 is a 1. So I'm going to say if Q does not equal a 1, display the error. Now, notice I can output the variables. I use %b to show that I'm going to put in a binary variable, and then notice after I close the parenthesis, or rather the quote, then I put the 3 variables that I'm outputting as these A, B, and C. Okay, then the next case is 0, 0, 1, and I want that output to be a 1. So again, I'm going to check if it's a 1. If it's not a 1, display an error. Okay, the other thing you want to note is this #10. That just means delay for 10 time units. So I set my test cases, I delay a little bit so the simulator has time to evaluate the circuit, and then I check the output to see if what the simulation evaluated is what I expected. And then once it's done with that, it gives the next test case and waits again and then checks it. So we want to do all 8 test cases. So I'm going to just go ahead and do a copy paste. Copy paste is very useful. However, you have to be careful that you change everything you want to change. Okay, so let's add some comments. This is test case 0, test case 1. Okay, so we've already did test case 0 and 1. 2, change to 2, and the Q we want for 2 is a 0, so 2 is a 0, 3 is a 1. Okay, once we've finished listing all of our test cases and what we expect is the output for each of them, we can display finished. Alright, so let's go ahead and save this. You can hit Control S to do that. Okay, so let's go ahead and run simulation. Okay, so now that we have an output Q, it's green. Let's first check our console to see if we have any errors. So notice we have the word finished and there's no error messages, so that means everything checked out. We can verify this also with the timing diagram. So if we open this up and zoom into the beginning, you can see here that when A, B, and C are all 0, the output Q is a 1. When A, B are 0, and C is a 1, the output Q is a 1, etc., etc. So the timing diagram verifies the same thing as the truth table. And so having the output tell you if there's an error or not is very useful, because sometimes it's annoying to stare at all these waveforms and just know if this works correctly or not. However, you may have made a mistake somewhere in your simulation file. Maybe you, when you copy pasted, you forgot to change an output Q to a 1 or a 0, and then it says you have an error when you really didn't. But at least it will point you to hopefully the right test case to see, did you make an error in your file, in your test file, or did you make an error in your module? Okay, so the very last step, now that we have a working circuit, is to put it on our basis board. So go ahead and close your simulation, and then we have to add a source. We have to add the constraint file. Now, once again, you only have to add the constraint file once to the project. Add or create constraints. And we will create a file, and we can call this basis 3 constraints. Let's go ahead and open it up. You can see that it's empty. What you can do is get the constraints from Polylearn, which is at the top, called basis 3 master. We'll Control A, Control C to copy it in to this file. Okay. So this is what maps your module to your board, and what we need to do is map our inputs to switches. So let's find out where the switches are. Here's some switches, and our output to an LED. So let's go ahead and map A to switch 0. So where it says switch 0, you can go ahead and put in A. You'll do that on both lines. And then we'll map B to switch 1 and C to switch 2. And then we need to uncomment these lines because we're using them. So I highlighted, right-clicked, and then go to uncomment. And then the LED for the output. And our output is called Q. So we'll put in Q for LED 0. And once again, uncomment that. And we can save. Alright, so once we have mapped our inputs and outputs of our module to the basis board, LEDs and switches, or whatever else we're using, we can move forward and run implementation. So now you hit Run Implementation. Say yes. Okay, once the implementation completed successfully, click on Generate Bitstream and click OK. Or you could also hit Generate Bitstream down on the left-hand side. Alright, once the bitstream has completed successfully, you can go ahead and put it on your basis board. So we can open the hardware manager to do that. That's also down here on the left. So make sure your basis board is attached to your computer and turned on. And then you can go to Open Target, Auto Connect. It should find your basis board. And then you would click on Program Device and find the bitstream file, which would be under your labs, runs, implementation, lab0.bit. Then you hit Program, and it all should be good. Alright, that is how you design a simple digital circuit in Vivado.